This is a revision video for P5g Refraction, dispersion of light, and total internal reflection. Refraction is the bending of light when it travels from one medium to another. This is due to the change in the speed due to the density of the material. Sometimes it can cause some unusual optical effects. Mirages in deserts are caused by refraction. Swimming pools look shallower than they actually are, and fish are seen from above the surface of the water and not where they appear to be. If light enters a denser material, for example from air into glass, it slows down and it bends towards the normal line. If light enters a less dense material, from glass to water, it speeds up and it bends away from the normal line. The refractive index of a material is a measure of the speed of light through that material compared to the speed of light in a vacuum. Denser materials have a higher refractive index. The refractive index of water is 1.3, the refractive index of glass is 1.4, the refractive index of salt is 1.5, and the refractive index of diamond is 2.4. This shows us that diamond is a very dense material because it's got a higher refractive index. For materials with a refractive index which is greater than 1, the angle of incidence is greater than the angle of refraction. Materials with a higher refractive index cause the light to slow down more and bend more towards the normal line. In the diagram, the one with the refractive index of 1.6 bends the light more towards the normal, so it has a smaller angle of refraction. The refractive index of a material can be found using this equation. Refractive index equals the speed of light in a vacuum divided by the speed of light in the material. The refractive index does not have any units. This is because the speed of light in a vacuum is metre per second and the speed of light in the material is metres per second. Therefore, these two units cancel out, leaving this quantity unitless. The speed of light is a constant. It's 3 times 10 to the power of 8 metres per second, or 300 million metres per second through a vacuum. However, when it travels through a material, it can slow down. In this example, the light travels through a piece of glass at 250 million metres per second. If we want to work out the refractive index of the glass, then we can use our equation, with the speed of light in the vacuum divided by speed of light in the material. If you do that calculation, it gives us a refractive index of 1.4 for the glass. Because the speed of light changes depending on the density of the material, it means that different materials end up with different refractive indices. If the material is denser, then the speed of light slows down even more. So that means we have got a smaller number dividing our speed of light, which ends up giving us a greater value for the refractive index. This diamond has got a refractive index of 2.4. What I'd like to do is stop the video and use that equation we saw in the last bit to find the speed of light through the diamond, and then I want you to think about which way the light will bend on entering the diamond. Will it go towards or away from the normal line? If you stop the video now, you can have a go at this calculation. On doing this question, you should have first written down the equation you need to use. Then you should start putting your quantities into that equation. You were told that the refractive index of the diamond is 2.4, and because the speed of light in a vacuum is a constant, it never changes, so you should have put 300 million for that value. This is the value that we need to calculate. On rearranging that equation, it gives us 300 million divided by 2.4, which gives us 125 million metres per second, or 1.25 times 10 to the power of 8 metres per second. And because the diamond is a denser material than the air, then on entering the diamond, the light ray should have been bent more towards the normal line. Now that we've done some examples, you can stop the video and have a go at using that equation even more. We're now going to talk about dispersion, and this is the way that we can form a rainbow from white light. When the light enters the glass, it slows down and it refracts. Different colours have got different wavelengths, so they are refracted by different amounts. When the rays leave the glass prism, they are refracted again, and this separates out all the different colours of the visible spectrum. The different colours travel slightly different speeds in the material. The shorter the wavelength, the more slowly the light travels through the material, so it bends more towards the normal. This means that the violet light bends more than the red light. It's got a shorter wavelength, so it slows down more. Remember though, that all the colours of light have the same speed in a vacuum. There are no rainbows in empty space. Because the different colours travel at different speeds through the glass, each of them has a different refractive index. Violet light travels slowest, so it has the largest refractive index. The red light travels the fastest, so it has the smallest refractive index. Here are some examples of the different colours and their refractive indices. And you can see that violet has the largest. White light is a mixture of all the component colours that we can see in the visible spectrum. The colours range from red to violet. The red light has got the lowest frequency but the biggest wavelength, and the violet light has got the highest frequency and the shortest wavelength. We usually state the spectrum in order from longest wavelength to shortest wavelength: red, orange, yellow, green, blue, indigo and violet. You can remember the order of the colours by using this rhyme. Richard of York gave battle in vain. We can observe the different colours of the spectrum when we see rainbows. The white light entering the atmosphere is refracted through the water droplets in the air, and it splits up into its separate colours. This is a dispersion effect. As well as rainbows, you can see dispersion in many other places, such as the lenses of microscopes and telescopes, fibre optic cables, and also sound waves can suffer from dispersion. If you stop the video now, you can have a go at some of these dispersion questions. You will need the equation we used earlier for refractive index. If you can't remember it, you might need to skip back a few sections and write it down before you try these questions. Okay, so now we've talked about refraction and dispersion, we're going to talk about total internal reflection. When light travels from one material to another, it refracts or bends. However, some of the light is always reflected from the surface of the material. If the light hits at a large enough angle from the normal, then all of the light is reflected back in. So none of it can pass through and be refracted out. This is called total internal reflection. If the light is below an angle called the critical angle, most of the light is refracted and can leave the material. However, there is some reflection. At the critical angle, some of the light is directed along the boundary of the two materials, with some of the light being reflected back in. However, if the light is travelling at greater than the critical angle, all of the light is reflected back into the material. The critical angle of a material depends on its refractive index. A denser material has a higher refractive index and so a lower critical angle. Here are some examples of critical angles for light travelling from the material into the air. You can see here that the critical angle for diamond is the lowest, 25 degrees. This means that diamond is the denser material. You can also see this from its refractive index, as it is the highest. Total internal reflection is very useful to us. It can be used in fibre optic broadband. Fibre optic cables are very fine and they're made of glass. They're used to transmit data as pulses of light. They're used in cable TV and broadband services. They're much quicker than using a normal phone line. Information can also be multiplexed, which means you can send a number of signals down the cable at the same time. Another use of total internal reflection is a laparoscope, a bundle of fibre optic cables that's inserted into a keyhole incision during surgery. Light is sent down the cable and illuminates the inside of the body, and then it is reflected back down separate cables to a screen where the image can be seen. Binoculars also make use of total internal reflection. The prisms in binoculars are designed so that light is totally internally reflected. This can then be used to produce a magnified view of an object and make sure that the image is the same way up as the object which is being viewed. Cat's eyes are another use of total internal reflection. The light from car headlights enters the cat's eye and is totally internally reflected back. The light then exits back the way it came and can be seen by the driver. Total internal reflection can also be used to make diamonds sparkle. Diamonds can be cut into shapes with many flat surfaces. These flat surfaces make maximum use of total internal reflection. They want the most light to come out through the top or crown of the diamond for maximum sparkle. Okay, now that brings an end to this revision section on P5g on refraction, dispersion and total internal reflection.